Welcome everybody to this talk. My name is Stefan. I'm going to speak about the stream processor as a database with Apache Flink. Let me quickly ask this. How many people here have a rough idea of what Flink is? So, okay, then I can assume a bit and don't have to go into the, I don't have to start very high level. Okay, that's actually good. All right, now let's get started with the actual talk. So talking about the stream processor as a database, I want to quickly start with this quote because it kind of sets the scope in which the Flink project thinks about stream processing. So the idea of stream processing in the scope of Flink is not stream processing as just some real-time notion of event processing, for some low latency complex event processing and so on, but it's really a very broad paradigm. It's a paradigm to build both real-time and non-real-time applications that just work in this continuous processing paradigm, where your data set is, it's not a static thing that sits there and never changes. It's a continuous data set that evolves over time, that's created over time, which is actually true for almost the vast majority of data sets, if you think about it, right? They get created over time as log records, as events of interaction, sensory events, and so on. So stream processing here as a broad paradigm, in fact, actually as a, if you wish, almost as a superset of batch processing. So before I dive into the specifics of the stream processor as a database, let me quickly give you 3 slides of background and overview on Flink, just to recap on the essentials. So Apache Flink is a streaming data processing system. Actually, in its core, it's a distributed data flow engine, actually, a fairly powerful and flexible one, on top of which it exposes 2 programming APIs, one for data stream processing, one for batch processing, data set processing. So to the system, everything is streaming. So the runtime is really built as a streaming engine. It keeps data moving as much as it can. It doesn't necessarily impose barriers, so it can achieve fairly low latency. And the data set and data stream APIs are, if you wish, just 2 different views on stream processing, because to Flink, batch is a special case of streaming. And the data stream API is an API that exposes really streams that can be infinite, can also be finite, and exposes all these utilities you need for streaming, like windowing, working with state, and so on. Batch processing is, in some sense, a little simpler than streaming. So in batch processing, you often don't have to worry about windowing and state and so on. All these things are implicit. So the batch API is kind of a simplified API for batch processing, and with a few additional constructs that come in handy when you do batch processing, like for block synchronous iterative processing, for example. And on top of these APIs, Flink exposes a set of libraries around graph processing, complex event processing, machine learning, and so on. So if you actually use Flink, what you do is you write, for example, in the data stream API, this is an example of the data stream API in Scala. You write these fluent functional programs that get transformed into these parallel data flows that then get executed in the cluster in a parallel fashion. So both are kind of 2 views of the same thing. So a program as a functional program, and a distributed data flow graph for execution. So I'm talking about a very specific part of Flink today, but in general, Flink is a fairly broad system by now. And if I had to sum up what makes Flink actually a very good stream processor, I would say it's sort of around these 4 corner points. That it's a true streaming engine at the bottom that keeps data moving, keeps it moving with low latency, so it achieves low latency, high throughput, very well-behaved flow control. It has a very good support for stateful processing, which is especially important for what we're going to talk about today. So it can actually give you exactly one semantics in the case of failures for state in the streaming computation. It has the notion of globally consistent save points, snapshots that you can take of the computation and use them to modify the program or upgrade the framework, or just fork of different variants of your streaming program. And it gives you this guarantee on user-defined state and on state you, for example, compute in, in time windows, count windows, and so on. It has very flexible support for Windows, so you can use basically almost all thinkable variants of Windows. Time windows, session windows, count windows. You can roll your own windows by defining a set of Windows assigners and triggers and so on. And one of the very important things I think in stream processing here is also the support for event time. Event time meaning Flink is able to actually work on events or correlate events by the time when they were produced by their sensors or by the services, rather than when they end up in the stream processor, which in many cases allows you to make a lot more sense of the data, and it also has the ability to actually decouple the results from the real runtime in terms of whenever you reprocess or when you work on historic data. You can do this with the exact same streaming program as you use for real time. It will give you both meaningful results in both cases. So with that as a broad overview of Flink, let's actually dive into one specific aspect for today. Using the stream processor as a database. So in order to talk about this, I'd actually like to motivate this with a use case. And while it may sound like something a little esoteric at first, why do you want to actually use the stream processor as a database? I mean, you have a database. What is that thing about using the stream processor as a database? While this may sound a little esoteric and initially, it actually, to make the motivation why this is very helpful, we don't have to go to a very complex use case. We can actually take almost the simple, most streaming use case that there is, and that is real-time counting and aggregating. So let's look at this classical example. This is just one motivating case. Assume you have a streaming application, something like Twitter, but it could just be anything, right? And any stream of events produced from an online shop, from monitoring a factory plant or whatever, and you want to create real-time statistics, be that counts, aggregates, outliers, and all of that. And this may be for the ops team as a dashboard. It may actually be a product you offer to customers. It may be input to real-time recommender that you use in your product and so on. So it's something I think that's a fairly pervasive use case in streaming, just computing real-time statistics. Let's build this in this classical streaming architecture, right? We have something that produces the events from our service, from user interactions with the service. We use something to log and to store the events. I've used Kafka in that example because it seems a very popular choice and it works very well with Flink, but you could basically plug in other message queues there as well. It's not tied to Kafka. The third step that we're actually talking about mostly today, analyzing, computing actually the aggregates. We're doing this with Flink, and then there's some way we want to, in the end, share the results with some form of database. Elasticsearch, Redis, MySQL, Cassandra, whatever. So given this broad setup, a simple, real-time statistics program could actually look as simple as that. That would almost be the entire program. Let me walk you very quickly through it. This is written in Flink's data stream Scala API. We're defining a simple type for impressions, which has a string ID and an impression counter. We're creating a data stream from Kafka, where we're taking our environment, adding a Kafka data source, and then we're doing some very simple pre-processing. So we're filtering out events that are not impressions, and we're mapping the events to an impression data type. The interesting part is actually the last part where we say group this whole thing by ID, window it by an hour, and then sum up the impressions. By the way, for those of you who know a little bit more about stream processing and are wondering now, this time window of an hour, what does that refer to? Is that processing time or event time? That's actually orthogonal for the example here. It could be both. It could be either, whatever you're interested in your specific use case. So where this is a kind of code view of this whole task, this would be, if you wish, the Dataflow view of this example. We're starting with a Kafka source, running through the filter, through the map. Then the data gets shuffled, reorganized by key. windowed, and in the end, in the sync, published in some way. Bear in mind, this is more like the logical view. Flink will actually condense some of these operators. So if you implement something like that, run it, and then look, for example, at the Flink UI, it will not show you all these individual bubbles because they get collapsed. All right. Let's actually look at, almost the complete picture then. This would be how we built this job. Consuming from Kafka, there's the first actual operator in Flink, the collapsed functionality of the consumer, the map, and the filter, the grouping, which involves the shuffling of the data. Then you have the window operator, and then I just picked the Redis icon here because that's what we actually used in our experiments here in order to publish the data. And the way this setup actually works is, we're computing aggregates over an hour, but in our dashboard that only shows the results from the previous hour. It's not a real-time dashboard. You also want to show the results, like the in-flight, the pending results of the current hour. How far have impressions, interactions come in the current hour? So something you'd have to do is you would have to sort of push out frequently your pending results, your in-flight counters, if you wish, also to this database to expose them to your dashboard or to your other application. So one way you could actually realize that in Flink is by using the window mechanism in such a way that you use a combination of a proper end of window trigger at the full hour, and you use periodic early triggers that just publish the window, basically flush the window to the sink, so you can look at the current counts. But the stream processor still keeps the count around, updates them, keeps updating them until the full hour has passed, and then it will actually emit the final result, the final count for the hour. That example is actually apparently so common that when a few months back Yahoo published this data stream processing benchmark that picked exactly that scenario. So I think there was a talk actually yesterday about the results from the Yahoo stream processing benchmark, and it was almost that. I think it was actually even Redis. It was not hourly windows, but I think 10-second windows or so. But other than that, it was almost like that. I also used Kafka, also used basically I think they had an additional like cache lookup or so, but other than that, it's pretty much the same. So given this example, let's actually look at how does it perform. For performance, I think there are three very interesting dimensions to look into. What kind of latency do you get out of that architecture or of that job and that implementation? What kind of throughput can you get out of it? And how can you actually scale it to a large number of keys? Keys meaning, in that case, unique things that you interact with, be this advertisement campaigns as in the Yahoo benchmark, be this tweets as, if you would run this on a Twitter-like use case, products if you would run it on a web shop where users interact with products or view products and so on. So let's look actually at each of these three dimensions, one after the other. So for latency, I'm just going to cite this Yahoo benchmark here because I think it was actually did a fairly nice job on this latency evaluation. The latency of these jobs, they set it up to run in 10-second windows and basically periodically flush the result every second. So what you get is you get a latency that's like around 1 second, and depending on how you tune the throughput, how you tune exactly do you flush everything, only the deltas, how many keys do you use, and so on. It can vary a little bit, but it's round about that ballpark. So let's say latency is actually, it's good in this application. If we have a dashboard that's, within 1 second accurate to whatever people are doing in your online service and so on, that's probably acceptable for most people. Let's look at the throughput. The Yahoo benchmark didn't go all that much into throughput, so we looked a little bit into throughput ourselves, and we ran this on a slightly different setup than Yahoo ran it. The most important thing about that setup is that the Kafka storage cluster and the compute cluster were kind of separate. So we were running it. We're basically using this the code from the Yahoo benchmark again, and we were running it with Storm Flink. And we're actually seeing that when we were running this with Flink, that the bandwidth between the Kafka storage cluster and the compute cluster were sort of becoming the bottleneck. And that's where we added a third variant of this job, where we basically we created a mock variant of the Kafka consumer that actually doesn't, pull from the other cluster, but like locally, it more or less generates the data in order to eliminate that bottleneck. And with that, we sort of got the throughput to a fairly large number, like 15 million on 10 machines, which is, I think, a fairly neat scale. So let's say throughput in that architecture also works well. Now the last interesting number was, how does it scale with different numbers of keys? And there, when we started out with a streaming benchmark from Yahoo, they really didn't want to actually take into account they really didn't want to create a bottleneck on the key value store, so they picked like 100 campaigns. So it was basically 100 keys that you computed aggregates for. If you think about many real-world applications, you probably have a lot more than these 100 keys. So if you just think about an example like running this in a Twitter-like use case, you're going to have millions or hundreds of millions of different users or products and so on that you interact with, and you'll have millions of interactions potentially per second that you want to handle. So let's actually look how this would behave if we go from 100 keys just to 1 million. We don't even have to go to hundreds of millions of keys. Let's just go to 1 million. And so the result was pretty depressing. So if you go from 100 keys to 1 million keys, the throughput drops from now 15 million to, I think, somewhere around 200,000 or so updates per second that you can make. So what's the reason for that? This seems like a massive drop, right? So where was the bottleneck in the end? And it turned out the bottleneck was not really in the stream processor. So it was nothing wrong with Flink or so per se. It was just the whole idea of every second pushing all the updates to the database. Because if you have 1 million keys and you're running at 15 million elements, even if you have some skewed distribution, you're going to have close to 1 million changed keys or so per second that you'd have to write to the key value store. And the key value store that takes a million writes persistently per second has to, you can do it, but you have to give it a good number of nodes. So in that case, we didn't use a large number of nodes. I think actually this was going against, in that benchmark, a single large Redis instance. And it just couldn't handle it anymore. And that is Redis, which actually at this, just write, fire and forget write operations extremely fast, like probably the fastest of breed. And even that couldn't handle it anymore. So that kind of led us to the point of saying, okay, what do we do about this? It doesn't really make sense to try and build a stream processor that can get very high throughput if there's actually no way to share the results with other services. If the typical bottleneck is actually somewhere else, and this bottleneck is hit a lot earlier, and in order to overcome this bottleneck, you would have to scale out the database so far that you'd have to throw so many resources at it that it almost becomes prohibitively expensive. So the idea that we had back then was something we called queryable state, and it's kind of the theme for this talk, the stream processor as a database. And the idea of queryable state is actually very, very simple if you think about it. Instead of every second trying and pushing out all the changes to a database, you really only do this in order to make it early accessible to your services. Why not let these services directly look into the counts that you have in the stream processor at that point in time? Because there's basically some materialization of all your keys with the current counts already somewhere inside the stream processor. Why do you want to make a copy of that, mirror it to the outside world, which is very expensive, just to expose it? This seems like something you only do because an interface is missing. And that is kind of the interface we thought was missing, being able to direct queries against the stream processor directly. So in this setup, you would direct real-time queries directly against the current content of the windows in Apache Flink. And at the end of the hour, for example, it could still flush the final aggregates to a database. If you're interested in them, if you say, by the time the hour's up, I'm anyways not interested anymore, then you wouldn't even have to do that. But in many cases, you could be doing this and say, I have an, if you wish, a kind of archive database that has the past results, where the windows, once they're done, flush the results, and then I have the real-time part of the queries that go against the state directly. So thinking about this, you will have, let's say if you have hourly windows, you'll have one flush of your key space per hour into the database, which is something much, much more feasible rather than doing it every second. So this seems like an idea that is so simple that it almost seems like surprising why nobody has been doing this. And I think the answer is actually that in order to do this, you have to have a stream processor, or you have to have support for state inside the stream processor that is powerful enough to handle this. In particular, you actually have to have something like first-class support for state in the stream processor, which has not been true for stream processors for a while, I think. Like, for example, for most of the time, I think, except for the latest version, Storm was essentially almost a stateless stream processor, unless you were using the Trident library, which was, but then again, not properly streaming anymore, but working in a micro-batching way. What is also really important is that the state is fault-tolerant and correct, because on a failure, you do want to recover it if you actually send queries against it. It should not get lost. It should not be some best effort thing that is around while it's around. If it's gone, it's gone. So it has to be around, and actually, ideally, it has to be strongly consistent with exactly one semantics. The state needs to be actually not something in a centralized service of the stream processor. It has to be something that is distributed with the computation, with the operations, so it shards with the operators, because that way you can actually scale it out. Otherwise, you would be defaulting to some non-parallel service again, which has limits in its scalability. The fourth point may actually not be very obvious, but in order to do this, it's actually very important that the data structures that hold the state actually stay around. So if you actually embed the state inside an operator, and the operator comes and goes every time because you're running in some form of mini-batch paradigm, then this is not very easy to do. And the fourth one is that the state has actually to be scalable state. So it has to be able to overflow the disk if it grows too large. It cannot just be a best effort hash map or so that you keep. So over the last months, actually, all of these things became available in Flink, and this is why actually this queryable state is I think a feasible thing to do now. What is the status in Flink in working on queryable state? So we've done basically a proof of concept. We've actually iterated over the implementation a couple of times. It's not yet in a release version, but the code is available in a pull request or in a branch, also with some design docs, with some evaluation and so on. And we're trying to like polish it, benchmark it, collect feedback on people who want to try it out and use it, and see how we incorporate that in future versions, expose it nicely in the APIs and so on. So if you're actually interested in trying this out, like now, you can actually go to the Flink project site and check out that branch and play around with it. So if we actually then rerun the same experiment using queryable state, so does it actually work? Yeah, that's what this slide is supposed to show. It works, and the result is actually not very surprising, because it gets you back to basically the exact same throughput as before, and yeah, and that is not surprising, because you all of a sudden eliminate exactly the thing that became the bottleneck before, because you're not flushing every second anymore to the database. So before, in the 100 keys case, writing these 100 keys was just no bottleneck. So the bottleneck was actually somewhere else. It was in the shuffles in the stream processor and so on. And eliminating that bottleneck again actually gets you back to the exact same bottleneck you had in the first row. So it seemed to have solved the problem. Yeah. If you're actually using this in an application, how do you have to write your application, shape your application to make use of that? And that kind of depends on what your application is exactly doing. So if you're really only interested in some real-time statistics and so on, then you would just say, instead of querying Redis, query Flink. You'd have to use the basically Flink queryable state client code for now to use that, but I don't think there's a fundamental reason why there couldn't be compatibility wrappers to just swap, for example, a Redis client library, or make it appear like a Redis client library so it works almost seamlessly. If you have something that is interested in both real-time results and historic results, then what this actually needs is something like a query service that's actually routing the query either to the archive database or to the real-time results. And for those of you who actually have worked with a Lambda architecture, this should look familiar. This is almost exactly what is behind some of these Lambda architecture tools, right? If you're actually interested in data computed by the real-time path, then you'd actually follow the part that is done by Storm and written into the real-time tables, for example. If you're interested in the more historic results, once for example the hour is up, then you would look at the data computed by your MapReduce job or so. So this there are actually quite a few applications that sort of have something like such a query service in place. All right, how did we implement this in Flink? And in order to explain this, let me very quickly recap the process model of Flink. So in Flink, there are basically three processes. The Flink program with a client process. That's once the client, that is one process. We have the so-called job manager, which is the master process. There's one in a non-available or non-highly available case, and there can be multiple ones, multiple standbys in a high availability case. And then there are a bunch of task managers. The task managers being the workers, the ones that actually do the processing, that work on the streams. And the client submits the program to the job manager. The job manager has something called the execution graph, which is the parallelized view of the data flow graph, which keeps track of in which status is each individual operation, which nodes currently exchange what streams, and so on. So this basically is done to track failures and figure out how to react to failures and so on, what should be sent where to be restarted and so on. And the task managers actually execute the individual tasks, and they have components like the memory manager and network manager to exchange data. So to add queryable state to Flink was actually not a very invasive thing. The majority of the complexity is, if you wish, actually in something like a client library. So if we want to now, let's assume we're sending a query. We want for a certain kind of ID, we want the current count. And it works a little similar as you think, lookup of a piece of data in HDFS would work, or querying in some of the distributed databases would work. The first thing is to figure out, where does that data that I'm interested in actually reside. So the first thing is actually going to the job manager. The job manager gets a new interface that allows you to query where the location of a certain state is, and that just looks up in the execution graph where that particular shard of the operator has been scheduled to. And that would basically expose that, make that available to the client, and then the client could directly go to the respective task manager and say, hey, I'm interested in basically that shard of that operator, that name of the state, that particular key, what's the current value associated with that. So the task managers actually, whenever an operator spawns a state, it can decide to make this available, to make this queryable, and then it would just register it at this state registry, which would answer the queries then. They go basically against the exact same data structure as the operators use when they update the windows, they update their current counts. That was basically all we had to do for this implementation. So there's a last part now in this talk where I'd like to actually look into how does this. So first of all, why is this actually fast? What is the secret sauce? Why can Flink compute this state at such a speed, and it seems so hard to do this with some of the key value stores? So what is kind of the difference? I would also like to sort of contrast this architecture with that of a parallel database a little bit. And you may have actually heard some of these thoughts. Martin Kleppmann has been giving a series of talks called turning the database inside out, where he was speaking about using like a log-centric, in that case Kafka-centric architecture to rewrite the classical data warehousing architecture into something based on Kafka and a stream processor. In some sense, the queryable state thing is, if you wish, like a continuation of these thoughts. I would say taking it one level further. But I'm going to use some of his terminology here. So in order to sort of start explaining this, let me start with what the typical distributed key-value store actually does. And this is a screenshot from the docs of Apache Cassandra. So if you write a piece of data, the first thing that it actually does is it will append it to a commit log. That is the most important operation, right? That means the data has been persisted somewhere, and if something happens, I know that there was this write operation, and I can redo it. The next thing is it's actually materialized in something called the mem table, which is the latest bit of changes to the table that you make the changes to. And once in a while, this mem table is actually flushed to disk into an SS table. It may be merged or compacted, is what they call it, with other tables on disk. And if the mem table is actually lost before it goes to disk, then it can be recreated from the commit log. So the commit log can only be discarded once it has been flushed to disk, and there's in addition the requirement that the changes have to be replicated to a quorum. So a sufficient number of nodes that you can get a majority consensus on a majority consensus on the fact that operation has actually happened. So if we now actually look at what is there, we see a surprising number of analogies to what we've just done actually with the queryable state. And let's go back to that picture real quick. Producing events, writing them into Kafka, analyzing something with Flink. So what you can think of is that the ground truth of this whole application is actually the sequence of the events here in the Kafka log. This is actually like the commit log in Cassandra, right? So there is actually a sequence of changes already persistently logged in this whole thing, right? So if you actually write it to a key-value store, and that key-value store logs it again and makes this change persistent, you're actually doing something that you've already done. And even worse, the fact that that the key-value store is actually tailored towards allowing multiple writes from multiple people and sort of replicating them individually, making them immediately visible is much more expensive than the way you would just append to a Kafka log, where you basically do the replication to your peers in order to keep it available. You do this in a pipeline in a streaming fashion as well. So just appending to a log, if you just do that operation by itself, very efficient in a Kafka-style way, you actually have that out of the way, and you don't even need to redo it in a key-value store. The next thing is the current contents of the window, so the current counter in Flink is almost like that mem table in Cassandra, right? It's something that you derive from the sequence of changes in the log, and then when Flink actually does its snapshots for fault tolerance, that's almost like flushing the SS table to disk, right? So we basically did all this already, and then you're writing to a key-value store who does the whole thing again, just to have the current view persistent. When you don't need that because you actually have basically built all of these things. And it's probably worth noting that we've sort of taken the support into different systems, and each system tries to just do this one thing in a continuous streaming fashion, optimized for throughput of streams, and not for multiple, like concurrent writers and making a change immediately visible in the presence of concurrent readers and concurrent writers. So, for example, if we actually look through how do modifications and persistence work in this architecture here, we have the events in Kafka. They're flowing into the sources, they're shuffled, and then they're changed into, they're exchanged, and then they're written into something called the state index in Flink, the state backend. In the case here, I'm making the example of using RocksDB, which is one of the choices you have in Flink. So, so this is basically all a continuous pipeline thing. So everything is in flow. There go changes into RocksDB all the time. And while one change is written, the other change comes already over the wire and so on. If we take a checkpoint, which is the mechanism in Flink to gain persistence, if a node goes down, how do we recover it? If we do such a checkpoint, it's an operation that's very lightweight in Flink. We just inject a barrier at the sources. We let the barrier travel through the topology, reach the stateful operators. At the point in time when they reach the stateful operators, we do if you wish, a state copy on write triggering, right? So that is something that you can, for example, do in RocksDB. You just tell it from this point on, actually, all changes that you make, don't overwrite something. Just create, if you wish, a delta, and then you can actually keep on working and you can modify the state, and in the background you have the original copy that you can persist to the snapshot. So it doesn't stop the processing. There's a little overhead, but almost no overhead on the throughput while this background persistence happens. And you can happily keep on changing that. And once the persistence is done, you actually release this snapshot, and it can be compacted away in the next compaction phase of RuxDB. So there's virtually no synchronous part in the whole persistence path here, right? If you wish, the almost only synchronous part is the initial writing to the Kafka log. If you want high guarantees there, then you have to sort of wait for some acknowledgements. But Kafka does a pretty good job, in overlying the writes and so on. So you can basically think that the whole part is pipelined, overlaid, and asynchronous, which is, I think, all in all the trick why you get this very high throughput. All right, we're almost at the end of the talk. To basically wrap it up, I think the takeaway from this talk should be that if you actually deal with stream processing and there are all these benchmarks on, here's the stream processor, here's what throughput I can get, bear in mind that is not the only bottleneck you should watch out for, right? The stream processor by itself, you can get those systems to the point that they have very high throughput by now, but that doesn't help you if actually the bottleneck in your specific case is the integration with external systems. So the idea of queryable state is one to mitigate one of the very big bottlenecks that we found. And it's a technology that works pretty well on Apache Flink due to its sophisticated support for state. In comparison to the other architecture, the performance of queryable state comes mainly from the fact that you try to do a very good separation of concerns. You do persistence with something which is really only tailored towards persistence of sequences of events like Apache Kafka, and then you do then you use the computation of the view over the event stream, the current counters, the windowing, and so on, with something that is really taking care, that is specialized towards this, like Apache Flink, and that makes imposes a very low overhead on the persistence of this aggregate view of the statistics. All right. With that, I'm basically at the end of this talk. I want to mention quickly two things. If you're actually interested in this whole space of stream processing and Apache Flink, there's a conference called Flink Forward in Berlin in September. Actually, submission deadline if you want to submit your own article is today. But the early bird deadline for tickets is it's in 1 week? One more week. It's 1 more week. I just heard it has been extended. Okay. The early bird deadline for tickets is still a bit to go. And if you think that this is kind of cool technology and you'd like to get involved more, then also contact us. We're Data Artisans. We're one of the companies who are helping push the development of Flink and helping users who want to make use of stream processing. And we're looking for people as well. Thanks. Minute and 10 seconds for questions, but everybody's, I think, running out for the lunch buffet.
Yeah, thank you. Excellent talk. So if I get it right, this is based on two architectural patterns. One is the partitioning state, and the second one, if we can say, the collocation of the state with where you query. So it happened in this case that it's identical. So if we think about partitioning the state gives local queryability. I did not see the word local anywhere in this talk.
Yeah.
And the second thing that I would like to focus on, you can get as close as possible to this one by using key value data store, which give you this collocation. So you can install, let's say in this case, no marketing specific tool, Apache Geo, for example. It has this capability of being application partition aware, and also you can collocate it with the stream processor.
Okay, that's actually an interesting comment. Yeah, let me quickly respond to that. One of the tricks here was, if we go back a few slides, exactly the fact that, all the changes here, is the slide still here? If we go back, one of the one of the big points here is, one of the important points here is that the changes happen only in a local data structure, right? So basically the complete write path is almost local inside Flink, right? You do the shuffle, but the shuffle is, pipeline streamed, overlaid and so on, and the modification is local. So the question is, can you actually in theory get the same thing by saying, okay, I'm trying to embed a distributed key value store that has this property that I can embed local shards into my application? You may get some of that, I guess. The other point that is actually pretty important here is that this way gives you very high consistency because this is integrated with Flink's snapshotting. So if a node goes down, it will recover exactly that snapshot of the state together with how much of the stream it will reprocess. So this is, with this tight integration, you get absolute strong consistency exactly once, which is something that is very hard to do if you actually embed a system that, for example, uses a different fault tolerance mechanism. And try to integrate it there. There are probably tricks you can play around and try and versioning and rollback and undoing changes and so on, but that's again going to be a bit more costly. So the second part that I think you don't get if you embed another sharded system is exactly this tight integration of the fault tolerance and persistence to give you the high consistency that you get here. But thanks for the comment. That is something I actually didn't mention in the talk.
How the restart works? So let's say process is already running, you have data in memories, stuff like
Yeah.
that. You want to stop it for maintenance, you want to restart within a minute. So how will the aggregation of the data already on how that piece works?
Yeah, so this whole thing is tightly integrated with, all right, I hear the message that time is up. Let me just respond to that question. That's the last one. It is tightly integrated with Flink's recovery mechanism, right? So for the time being, it is actually the case that if a Flink operator goes down, and for the time while this operator is recovering, you'll not be able to query it. So for many cases, this recovery is fast, so this downtime should be very short. If you actually want to, let's say, you want to migrate the stream processing job to a new job or to a different cluster, and you want to make this with as little interruption as possible, there's a feature in Flink called save point. So you could basically tell the system, okay, take a snapshot of exactly what it is right now. You start a new job on the new cluster from the save point, you let it catch up with the old one, and then you just flip the switch and say, work on that one. It is something that involves a bit of a few manual steps. I think you have all the tools you need to do it. It is something that, yeah, we may actually think about making this more automatic in the future, but for the time being, you have the blocks, but have to do it manually. Let's actually meet somewhere here and talk in person because I think they're throwing us out, okay?